Our next video is on volumes by cross-section. We are still going to be forming these three-dimensional shapes, but we're going to be doing it in a different way. And I'm going to show you a demonstration in just a minute. But whereas our shapes before were taking these areas and revolving them around certain lines, which created these circular cross-sections where you could kind of cut into it and see a circle, the cross-sections we're going to look at in this case are not necessarily circles. I don't think we're ever going to look at cross-sections as circles in this type of example. So instead we use different shapes to form these volumes, and I'll show you, like I said, I'll show you what I mean in just a second. So the shapes we were seeing before were more rounded shapes like funnels and cones and cylinders and things like that. They had to be rounded because as you create this sweeping motion of a revolution, it creates this rounded shape, whether or not it was, like I said, a circle or a cylinder or a cone or whatever the case may be. So with cross sections, it's a little bit different. So here is an example of a cross section. So you guys can see the area in the bottom. It kind of looks like the square root function. But notice instead of revolving it anywhere, we're taking these semicircles and we're just kind of plopping them in the area one after the next. And as it gets bigger, the semicircles get bigger. And together, if you look at them all, they create this volume. And so it is still a volume. It's still this three-dimensional shape, but it's just not the same type of volume that we were looking at with revolution. So again, notice a couple things that are changing. Number one, we are going from left to right, so looks like it starts at 0 and maybe stops over here at 4 or something. So our job is going to be to find the expression for the area of one of these semicircles, and if we can find the area of one semicircle, then we can have the integral add up all the areas together for us to find the volume of all of them being added together. So semicircles, that's one of the shapes we're going to work with. Another example is this one. So we can start with the base that's a triangle. Notice how they're generating cross-sections, and these cross-sections look like they are squares. So we put the base of the square inside of the triangle. So again, if we can find the area of one square and we just integrate from left to right, it will add together the area of all the squares for us so that it will create this three-dimensional volume shape. So kind of interesting how it creates that three-dimensional shape when you stack a bunch of objects next to each other. Let's look at another one. Here's some that are made with triangles. So you guys can see we have this arch from sine, and then they're going to take these equilateral triangles and put equilateral triangles in the base. Again, if you can find the expression for the area of one equilateral triangle, you can have the integral add together all of them for you. So kind of an interesting thing that it's creating, an interesting shape it's creating that we're going to find the volume of. This one kind of looks like an amphitheater. Let's see if there's any more that are interesting enough to show you. Here's another one with that same shape but with squares. Here's a circle that we're filling in triangles with, etc., etc. So there's a demonstration of kind of how it works and what it looks like. Let's get started on actually doing it. It says, find the volume of the solid whose base is bound by the lines y equals x minus 4, y equals 4 minus x, and x equals 0 with the indicated cross sections that's taken perpendicular to the x-axis. So first thing we probably want to do here is we want to draw a picture. I'm going to white out some of these other ones just so that we can get a good idea of what this picture looks like. So y equals x minus 4 is this line. Y equals 4 minus x is this line, and it's bound by x equals 0. So if I could do some highlighting, that's that one. This is this one. And this one is this. So this is the area that we are going to be putting our cross sections in. Now keep in mind that they are perpendicular to the x-axis. So perpendicular to the x-axis means they're going up and down this way. So for example, for putting squares, it would be like putting one, we'll start over here, putting a little square right here, and then putting a little bit bigger one right here, and a little bit bigger one right here, just like we were looking at in that video, where you're stacking these squares next to each other, and they're getting bigger and bigger as the area on the bottom is getting bigger and bigger. Now, because they're all perpendicular to the x-axis, everything is going to be in terms of x. My functions will stay in terms of x, my limits of integration will be in terms of x, my integral will be in terms of x. If we start going perpendicular to the y-axis, we would start stacking them this way. So you would start to see everything changing to being in terms of y if we did that. Excuse me. So I'm going to draw one square. I'm going to erase these highlighters just so it's easier to see. I'm going to draw one square to the best of my ability. It looks something like this. It's not perfect, but there's my square. So hopefully you can kind of visualize that it's coming out of the page at you. And the base of the square is touching both sides of these triangles. And then, like I said, it comes out of the page at you, and there's a bunch of them stacked up right next to each other as we go from left to right. So what we need to do is, if we can find the area to represent one square, then we can take our integral and integrate from the furthest point to the left all the way to the furthest point to the right. And the integral will add together the areas of all of the infinite number of squares that we could fit in that interval from 0 to 4. So the area of a square, first let's talk that. Area of a square is side squared. So essentially, in order to figure out the length of the side, I need to be able to figure out how long one of these sides is. So the way we're going to do that is we're going to look at the piece of it that's in the bottom of the shape, so the one that's actually touching the area that we're looking at. And the same way we found the length of a side when we were talking about like the rectangles for area between two curves, and also the same way we were finding the lengths of the radii in the last section when we were talking about volume by revolution, is the same way we're going to find the lengths of these lines. So essentially, if I want to know how long this side is, I'm going to do top function minus bottom function. So the top function is 4 minus x. The bottom function is x minus 4. So for the area, the side length is 4 minus x minus x minus 4, and then squared. Because one of these things in here represents the length of one side, and if I want to know the area of this square, I would just need to square it, because the area of a square is side squared. I could do a little bit of simplification here. I could do area is equal to, if I simplify inside of here, I get 4 minus a negative 4, that turns into 8. And then negative x minus x is minus 2x squared. And to find the volume, notice that we don't need any pi's in this one, because on the last one we only needed pi since we were evolving it and creating these circles, but that's not how we find the area of a square. The area of a square is a standalone function like this. So the volume is just going to be the integral from left to right. So the furthest point to the left is 0, the furthest point to the right is 4, and then of the area, dx. You could write it like this, you could also write it like this, the integral from 0 to 4 of 8 minus 2x quantity squared dx. Either one of those is fine with me. Why don't you go ahead and get out your calculator and try that one now. I'll put my video on pause. So pause yours, put that in your calculator, and see if you get the same answer as me. Alright, when I put in my calculator, I got 85.333. So the area by cross sections with squares filling in those places is 85.333. Alright, let's try this again, but the next one we're going to do is with a different shape. So let me erase this, see what our next shape is. Alright, our next shape we're working with is semicircles. So let's look at the same thing but with semicircles. See if I can erase the square I already drew. There we go, that's good enough. So a semicircle, the base is still here in the base of the triangle, or the base of the shape, but the top of it doesn't look like a square anymore. Now it looks like a semicircle, which is a half circle. So to find the area of a semicircle, the area of a semicircle is pi r squared, which is the area of a whole circle, but then divided by 2, because it's only half of it. So what we need to figure out is that we need to figure out how to represent the how to represent the radius of this semicircle. So if I draw it in red, the radius of this semicircle is from here to here. But that only works because this is actually a perfectly symmetrical shape. Now, if this line was like, it didn't have the same slope or whatever the case may be, then the radius might not be to the x-axis. The radius might be somewhere else. So the way that we're going to represent the radius is I want to look at this whole thing, the diameter, which we already know the length of because we found it in the last example. If I can find the length of the diameter and then just divide it by 2, that will be the length of the radius. So like I said, it happens to be symmetric in this case, so we could do top function minus bottom function, but I don't want to have you think that that's always the case, because like I said, if it's not a symmetric shape, then the way to find the radius would be to take the entire length and then divide it by 2. So we already said that the entire length for the diameter was 8 minus 2x from the last example, and then if you divide it by 2, then you get 4 minus x. Now, especially with semicircles, I see students doing this one wrong all the time, because it can get confusing with like the divided by 2's here, right? And then you also have to divide by 2 here, and I've seen students make that mistake a lot. So I will give you some words of advice. If this was me doing this problem, I would write down the area of a semicircle to show the reader that I know how to find the area of a semicircle. Then separately, I would write down the expression that represents the radius, and I would leave it like this. I would leave it 8 minus 2x over 2, and I wouldn't even simplify it to 4 minus x, because if you do that wrong, automatically they got to mark you wrong. So I would leave it like this, 8 minus 2x over 2. And then I would show them that I know how to find the area, or sorry, the volume by cross-section. I would write volume equals the integral of left bound is 0, right bound is 4, and I would just put area dx. That way, when I write my answer, my reader knows, oh, this person knows how to find the volume by cross-section. What did they say A was? Oh, they know how to find the area of a semicircle, pi r squared over 2. What did they say the radius was? Oh, they know how to find the radius of this semicircle. It's 8 minus 2x over 2. Did they get the correct answer? Yes? Okay, great. Then they know how to do all the pieces. They don't necessarily have to write them together. Because look what this looks like if you decide to write it together. 0 to 4 of pi r squared over 2, where r is 8 minus 2x over 2 quantity squared, dx. That's how you would have to write this if you wanted to write it all together. And like I said, you might think to yourself like, oh, I could do that. That's not that hard. I could totally figure that out by plugging in 8 minus 2x over 2 here to r and then plugging this into this. But you would be surprised when you go quickly in problems how easy it is to make mistakes when you're writing things. So I will leave it up to you. I know some of you guys have preferences one way or the other about how you want to write it, but if it was me, I would leave them separate. Just write them close enough to each other that your reader can actually figure it out, or like draw circles or arrows or something. But you don't need to write it like this, especially if you're going fast and you might make a mistake. And like I said, guaranteed mistakes will be made. So put this in your calculator, go ahead and pause your video, and then come back when you're ready to check your answer. All right, so I got 33.510 as my volume by cross section when the cross sections were semicircles. All right, let's try another one. Okay. We did squares. We did semicircles. I forget what the next one was underneath this. Let's see if I can undo this and then bring it back. Equilateral triangles and isosceles triangles. Okay, equilateral triangles. An equilateral triangle is a triangle that has all sides equal. There's my best version of an equilateral triangle. To find the area of an equilateral triangle, the area of a triangle is base times height divided by 2. Now, the base is the same length we've been finding, which is top function minus bottom function. That's 8 minus 2x. The height, however, of an equilateral triangle is not necessarily 8 minus 2x. If I can draw an equilateral triangle over here so you can see it. to find this height of an equilateral triangle, we would take the 8 minus 2x and then split it between these two sides so that each of these would be 4 minus x. And from special right triangles, you guys can't see that down there. It was 8 minus 2x. I split it between each side and it's 4 minus x. The special right triangles say that this is a 30, 60, 90 right triangle. 30 degrees, 90 degrees, and over here in the corner we have 60 degrees. So in a 30, 60, 90 right triangle, the shortest side, to get to the hypotenuse, you would double it. So this would be 8 minus 2x. Not that we need that, but in case you were curious. And then this middle side right here is taking this shorter side, 4 minus x, and multiplying it times radical 3. 4 minus x times, oops, not square root of x. 4 minus x times radical 3. And that's the length of the height, or the measure for the height. So up here, it's 4 minus x times the square root of 3. And that's all over 2 for the area of the triangle. By the way, this problem doesn't come up very often on the AP test. They don't ask you to memorize special right triangles too often. I have seen it, but it's just not one of the popular ones. The popular ones are squares, semicircles, rectangles, possibly isosceles triangles, so we'll look at that one next. Alright, so my volume formula. Volume is equal to the integral from 0 to 4 of the area dx. I'm not going to rewrite this in here because I already wrote my area up here, so I'm just going to leave that as is. Go ahead and pause your video, put that into your calculator, and see if you get what I get. Alright, in my calculator, when I put that in, I got 36.950. And last but not least, let's do this with isosceles triangles. Now, it didn't specify it in this problem, but with an isosceles triangle, we just know that two sides are equal. Now, we wouldn't necessarily say that the two sides that are equal are the ones that come out of the plane, because we wouldn't know how tall you would want them to be. So typically with isosceles triangles, when they say that two sides are equal, they say that one of the legs is in the base, or that it is the base. So typically you would see it like this. If two sides are equal, we would see it written like that, where these are the two sides that are equal. So in this case, the area of the triangle would be base times height divided by 2. The only difference is that base and height are the same because this is an isosceles triangle. So remember we said the base, the length of this was 8 minus 2x. So that's 8 minus 2x squared divided by 2. And then volume is equal to the integral from 0 to 4 of that area dx. Go ahead and pause your video and put that into your calculator and see what you get. Alright, so when I did that, I got 42.666 or 42.667. Alright, we're going to do one more problem in this video, which is an AP type question, and then we will stop there for today and pick up the rest of this tomorrow. Now, this is a previously released free response question, so keep in mind that this came from a free response test. Notice that it's number 5, which means it's a non-calculator section. Now, you might be looking at some of these things and thinking, oh goodness, I really don't want to have to work with those in terms of not using my calculator, but you'll see in this case that it's actually not that bad. It says, let f of x equal this quadratic, and g of x is equal to 4 cosine of 1/4 pi x. Now, the first thing we need to be able to do is identify which of these two functions is which, because if we can't do that, we can't figure out which one's on top and which one's on bottom. So, a quadratic function with a positive leading coefficient is facing up. So I hope it's obvious that this one is that quadratic, so that's f of x. And cosine typically starts up here at 1, or in this case 4, since the amplitude is 4, and goes down. So this one is g of x. It says, let R be the region bound by the graphs of f and g as blank, blank, blank. I cut out some of that directions that we didn't need. Part C. So notice that there was already 2 parts before this. We got down to part C. It says the region R is the base of a solid. So this is the base of a solid. For this solid, each cross section that's perpendicular to the x-axis is a square. So remember, perpendicular to the x-axis means that everything stays in terms of x. And they're squares. So let me draw one of these squares. All right, there's my square. So you can imagine they have a bunch of little teeny tiny squares all lined up next to each other that form this solid figure. It says, write but do not evaluate an integral expression that gives the volume of the solid. So the part that's not that bad about these equations and what we're doing here is that we don't actually have to find an answer for the integral. We just have to write out what the integral would be to show the volume. So remember, to find the area of a square, the area of a square is side squared, which in this case, the length of one side that's in the base would be top function minus bottom function. And top function is g of x, bottom function is f of x. So this is g of x minus f of x squared. And if I want to prove to my reader that I know how to find the volume, I'm going to say volume is equal to the integral from left to right. The furthest point over here is right up here, which is at x equals 0. And the furthest point to the right over here is at x equals 2. So my limits of integration are from 0 to 2 of the area dx. And as long as this is written close enough to that they're able to see that, then that is the correct final answer. And here's how I would probably notate it. I'd probably say, hey, here's my volume formula. This is my final answer. The integral from 0 to 2 of the area dx. And here's my expression that I use to represent the area of one square, g of x minus f of x. Notice that you don't even have to write the equations. You can just write their names, and that gets you full credit. So we're going to stop there for today. We'll pick up tomorrow.